Okay, so then we'll come back. So this part is related to contrapositive and converse. So contrapositive and converse is also supposedly something that you need to know about and is used extensively in mathematical reasoning. So of course I don't really know. I've never actually seen contrapositive used anywhere, but converse is used extensively in theorems and things like that. For example, you say that if, for example, in geometry, you say that if basically if two sides of a triangle are of the same size, are of the same length, then you will call that triangle an isosceles triangle. So in an isosceles triangle, these two base angles are equal. So then you can say that in an isosceles triangle, I don't know how to write the word isosceles. Isosceles or something like that. Isosceles, okay. So then you can say that in an isosceles triangle, the two base angles of course I'm not using the words that I'm using here are not very basically the words that I'm using here are not very precise, but you understand what I'm talking about. So so what I'm saying is that in an isosceles triangle, the two basically, for example, base angles, the two base angles are equal in size, are equal in measure, for example. So what I'm saying here is that when I say in an isosceles triangle, this is again an if-then basically kind of thing, meaning that if a triangle is an isosceles triangle, isosceles triangle, then the two base angles are equal. Okay, so if a triangle is an isosceles triangle, then the two base angles are equal. And of course you have to prove this in geometry, and then you use it as a theorem. Now suppose that in the same problem, in geometry you somehow prove that for example, if these two angles are equal, then these two sides are going to be of the same length. Then you can say that if in a triangle the base angles are of the same measure, then the triangle then the triangle is an isosceles triangle. Is an isosceles triangle. And I'm saying is an isosceles triangle, meaning that these two sides are the same, and then by definition, in a triangle that has these two sides of the same length, then you call it an isosceles triangle. Now, if you pay attention to these two statements, you can see that what I'm saying is that if a triangle is an isosceles triangle, then the two base angles are equal, and if in a triangle the two base angles are equal, then the triangle is an isosceles triangle, meaning that these are the exact opposite of one another, meaning that here I'm saying, for example, if P then Q, over here what I'm saying is if Q then P, if Q then P. So you can combine these two statements together and write it as if, basically not if, but you can write it as P if and only if Q. What this means is that, what this basically means is, or how you're supposed to read this is, P if and only if Q. Meaning that if P is true, then that means that Q is true, and if Q is true, then that means that P is true. And that is basically called, I don't know why I talked about this here. I suppose this is a part of here, but what I meant to say was that, for example, in the case of these two examples, if I call this, basically this situation down here is called the converse of this situation over here. Because what I'm saying here is that if a triangle is an isosceles triangle, then the two base angles are equal. And over here, what I'm saying is that if the two base angles are equal, then the triangle is an isosceles triangle. So then these two are called the converses, of one another. Okay? So now let's go over the text over here and see what we can find over there. And we have a couple of examples as well to basically work through as well. Okay, so now the contrapositive and converse are certain other statements which can be formed from a given statement with if-then. So that means that if you have an if-then statement, then based on this statement you can write the contrapositive of this statement, or you can write the converse of this statement. Okay, so these are the two things that you can write based on an if-then statement. So as an example, you can say that, for example, if the physical environment changes, that's an example. If the physical environment changes, then the biological environment changes. Then the biological environment changes. So the example is, if the physical environment changes, then the biological environment changes. Now the contrapositive of this statement, is if the biological environment does not change, meaning that if we take this part, if you take basically this part as P, and if you take this part as Q, including this part over here, now you can think of this as if P then Q. If P then Q. Now the contrapositive of this, is going to be if not Q, then not P. If not Q, then not P. So that's basically the that would be the contrapositive of if P, then Q. So in the case of this example, for example, you would say if the biological environment does not change. Now over here we have changes. You have to negate that statement. So I say if the biological environment does not change, then the physical environment does not change. Then the physical environment does not change. Okay. Now the interesting thing here is that these two statements are supposed to convey the same meaning that over here I'm saying if the physical environment does not change, then the biological environment, if the physical environment changes, then the biological environment changes. Okay, so again, these two, this statement over here, if P then Q, and if not Q then not P, which is the contrapositive of the first one, these are supposed to convey the same meaning based on what's written over here, meaning that now the same, basically conveying the same meaning. I don't know how to make sense of that phrase, convey the same meaning really, but we can try. But you need to, again, in such cases, you need to make sure that you're not making wrong assumptions, or you're not understanding things in ways you're not supposed to understand them, because sometimes you make some assumption, or you think that you have understood something, right? And there are you could actually find many proofs to prove that the way that you have understood that thing is actually right. For example, let's say that you're solving a problem in mathematics, for example. You're solving a problem, and the solution, the different steps in the solution has not been given to you. Only the problem has been given to you, and then in the solutions only some answer has been given, that, for example, when you solve this problem, the right answer is 27. But you don't know about the steps that you need to go through in order to solve that problem. Now, chances are that you start solving that problem, and you get to the wrong answer, meaning that you get to some number which is not 27, right? So, and assuming that the problem can have only one possible right answer, so then of course you can conclude that you have solved the question wrong, and then you can start over and somehow try to solve the problem right. Now, what happens is that sometimes it's possible in the case of in the exact same situation, you could have the problem and you could have the solution, but you don't have the steps that you have to go through, or you don't have the logic that you have to use in order to solve the problem. And it's possible that, well, out of coincidence or bad luck or whatever you want to call it, you might actually use the wrong steps and the wrong logic, but you might somehow it doesn't happen that often, but it can happen. You might use the wrong logic or the wrong steps or even the wrong techniques, but you could still get to the right answer. And then based on the situation, you would simply say that, well, okay, the way that I solved the problem was right, and then therefore I can use it in the future for other similar problems. So there you have no way of verifying whether your steps were actually wrong or right. Again, it doesn't happen that often, but it does happen sometimes. Now, referring to this situation, now you have learned something, or you have learned something. You think that what you've learned is right, but it's actually wrong. And if you apply it to some other similar situation, you might actually, you will actually have the wrong result, because the way that you solve the problem is wrong. Now, especially in the case of this part, which is mathematical reasoning, the material has been, and I think that's the only way to represent the material. Otherwise, it wouldn't be possible to actually represent the material at all. The material has been represented in such a way that you could actually make a lot of different types of wrong assumptions about what you read. For example, in the book over here, it says that note that both these statements convey the same meaning. This is statement and this is statement. Now, convey the same meaning, this sentence, there is many different ways to understand this phrase, convey the same meaning. In what sense, right? There is no way to know what they meant by this part. So you have to be cautious in these cases. Otherwise, it's really not cool and really not nice to learn something wrong. And because then later to get rid of it is in many cases, in many types of situations, very hard to get rid of something wrong that you have learned. Because when you learn something, then based on that you will learn something else. Based on that you will learn something else, and so on. The whole thing is basically connected together. Now, if one of those, it's just like, for example, some loops that there is a loop over here, then you put another loop in that loop, then another loop and another loop, and the whole thing is looped together, right? Now, if one of those loops is wrong, based on wrong assumptions or whatever, in however way that has happened, if one of those loops is wrong, then what happens is that then the whole thing that you have done after that is going to be useless. Meaning that then you have to do the whole thing again, meaning that you have to go back to the wrong loop, get rid of that loop, and then once you get rid of that loop, everything that you have built after that loop will simply fall down. And then you have to again go back to that loop, and then again start building loops and loops after one another in such a way that your logic is right? So So what I mean to say is that in such cases you need to be cautious, not make wrong assumptions or not learn wrong things, basically. Now, so now what this means is that it says that this basically now both these statements convey the same meaning. So let's see what that means, or what that could mean actually. So it says that if the physical environment changes, then the biological environment changes. If the physical environment changes, then the biological environment changes. Now the contrapositive of this statement is if the biological environment does not change, then the physical environment does not change. Okay? Now you just hold on to this, and now you need to kind of verify this with the other cases that you might get. Otherwise, now I don't really know how to make sense of this situation, because there are many different ways to do so. So now you hold on to this, and then you need to somehow try to make sense of this situation and see how you can safely make sense of it. So now let's go and do a couple more examples here. So you want to write the contrapositive of the following statements. And of course we don't have any. Okay. So for example, let's say that you have, if a number is divisible by 9, if a number is divisible by 9, then it is divisible by 3. Then it is divisible by 3. Okay? So your statement is, if a number is divisible by 9, then it's divisible by 3. Okay, so the problem that the example that we had over here is, if a number is divisible by 9, then it's divisible by 3. And you want to find the contrapositive of these statements. So we said that basically if P then Q, if P then Q, then what we do is to get the contrapositive, and at this point we really don't know what that can be used for, and what it's good for. But that's what's important is that then in logic there is all kinds of mathematical logic. For example, there is I suppose even in Boolean algebra and that sort of thing, all of these things will come together. I'm not sure, but we will see. We will have to go a little bit forward and see what happens with all of these things. But at this point, well, the only important thing is that you need to know what the contrapositive is and how you can actually, for example, calculate it. And so if P then Q, or basically P implies Q, then the contrapositive of this would be, if not Q, then not P. If not Q, then not P. Okay, so open my window. So what that means is that what I can say about this statement and find the contrapositive of it is that I need to say if if a number is not divisible by 3, then it's not divisible by 9. So if a number is not divisible by 3, I don't want to write too much. If a number is not divisible by 3, the negation of this statement, of the second statement here, divisible by 3, then it is not divisible by 9, which of course happens to be true as well. If a number is not divisible by 3, then of course it cannot be divisible by 9. Or as another example, if you are born in India, if you are born in India, then you are a citizen of India. Then you are a citizen of India. So to write the contrapositive of this, then you say if you are not a citizen of India, then if you are not a citizen of India, if you are not a citizen of India, then you were not born in India. Then you were not born in India. Or example number 3 is if a triangle is equilateral, if a triangle is equilateral, it is isosceles. It is isosceles. So then you can say that if a triangle is not isosceles, if a triangle is not isosceles, then it's not equilateral. Then it is not equilateral. So again, basically all of these examples, what they show is that the statement if P then Q, if your statement is P then Q, then the contrapositive of this is if not Q, then not P. That is basically in all of these cases we had basically this was the main thing that we were doing. Now the next thing that we have is the converse. And in the beginning of this video, I suppose I talked about the converse. So the converse of a given statement, if P then Q, the converse of this is if Q then P. the converse of this is going to be if Q then P. So if you have if P then Q, then the converse of that would be if Q then P. So for example, if you have this statement here as if a number is divisible by 10, it is divisible by 5. If a number is divisible by 10, it is divisible by 5. So then the converse of this statement would be if a number is divisible by 5, it is divisible by 10. So you write it as if a number is divisible by 5, divisible by 5, then it is divisible by 10, which is of course not necessarily true, but so as another example, we have, you want to write the converse of these statements. For example, let's say that you have if a number n is even, if a number n is even, then n squared is even. Then n squared is even. So the converse of this would be if a number n squared is even, then n is even. So the converse would be if a number n squared is even, then n is even. If a number n squared is even, then n is even. So then, or as another example, let's say that you have, if you do all the exercises in the book, if you do all the exercises in the book, you get an A grade in the class. You get an A grade in the class. And the converse of this is going to be if you get an A grade in the class, then you have done all the exercises of the book. Okay. Now the next thing that we have here is if two integers a and b are such that a is greater than b, if two integers a and b are such that a is greater than b, then a minus b is always a positive integer. Then a minus b is always a positive integer. A positive integer. And the converse of this would be if two integers a and b are such that if two integers a and b are such that a minus b is a positive integer, then a and b are then a is greater than b. Then a is greater than b. And that's basically all of these examples. And there is one more thing here that we can discuss, one more example. And let's go through this example as well. Okay, so the next example that we have is for each of the following compound statements. First, identify the corresponding component statements, then check whether the statements are true or not. So for example, if you have, suppose that you have, if a triangle ABC is equilateral, if a triangle ABC is equilateral, then it is isosceles. So what you want to do here is that first, this is a compound statement, and you want to basically identify the corresponding component statements. So the component statements, you can, if you think of them as P and Q, they will be basically triangle ABC is equilateral, or let me write it this way. That would be triangle ABC is equilateral, and then the triangle ABC is isosceles. Triangle ABC is isosceles. So these are the component statements of this compound statement, and of course, if a triangle is an equilateral triangle, then it is of course an isosceles triangle. So this statement is of course true. Or as another example, we have if a and b are integers. If a and b are integers, then ab is a rational number. Then ab is a rational number. So the component statements related to this compound statement are basically P, A and B. A and B are integers. And Q, AB is a rational number. AB is a rational number. And of course you know that the product of two integers is always an integer. And an integer is always of course a rational number, because for example, suppose that you have 2 times 3. These are 2 integers. It's equal to 6. This is an integer. Now 6 is the same thing as 6 divided by 1, which is of course a rational number. It's a rational number. And any other example that you take, you will have essentially the same result. And of course you can prove this as well, but that's not the point here really. The statement is true. Now there is something else called if and only if, which I talked about in the very beginning of this video. And if and only if is if and only if. That is represented by this symbol. Meaning that it's a two-way implication, meaning that, for example, if you say P implies Q, that means that P implies Q. If you say Q implies P, that means that, well, Q implies P. Now if P implies Q and also Q implies P, then of course you can say that P if and only if Q. That means that P implies Q and Q implies P. And there is now, this is in simple language, but more formally you can say that, basically if and only if represented by this symbol means the following equivalent forms for the given statements P and Q. That means the following equivalent forms for the given statements P and Q. Now what that means is that number 1 is P if and only if Q. Now, I don't understand really what this part really means, or what is really meant by this section. P if and only if Q. So the sentence that I see here is basically if and only if represented by this symbol means the following equivalent forms for the given statements P and Q, which makes no sense as far as I can understand. But then the equivalent forms are these: P if and only if Q, Q if and only if P, Q if and only if P, and then you have P is a necessary and sufficient condition for Q and vice versa. So you can say that Q is a necessary and sufficient condition. P is a necessary and sufficient condition for Q and vice versa. And that also, well, another form is this one, which is P if and only if Q. That's written this way. Now let's see if we can make sense of this in the examples, because we essentially understand what that means, but there is only this part over here that we need to probably go back and take a look at, and that is what does it mean for P to be a necessary and sufficient condition for Q. This is important, and I seem to have forgotten that, because there was some example over there. We learned this through an example. So let me go back and take a look at those things. There was somewhere over here. Okay, so we had some part over here that we said that basically we had an example over here. We said that basically we had two statements which were a number is a multiple of 9. So the statement P was a number is a multiple of 9. Is a multiple of 9, and Q, a number is a multiple of 3. So a number is a multiple of 9 and a number is a multiple of 3. Now in one of the if we have basically these two statements, then if P then Q, basically we said that it's the same as these following, basically is the same as the following. And in one of those, basically in one part, we said that Q is a necessary condition for P. Q is a necessary condition, for P. So what that means is that when a number is, so if Q is a necessary condition for P, what that means is that when a number is a multiple of 9, it is necessarily a multiple of 3. So when we say that Q is a necessary condition for P, so what that means is that when a number is a multiple of 9, it is necessarily a multiple of 3. That's what this means. And when you say it, basically, for example, some statement is basically a necessary and sufficient condition for some other statement, what that means is that, well, the first part, the necessary part, we already discussed over here. And sufficient means that that's the only basically condition that you need for the other statement to be true. Meaning that, for example, if I say, in this context, if I say Q is a necessary and sufficient condition for P, so the necessary part, which we had over here as well, the necessary part means that basically if a number is a multiple of 9, it is necessarily a multiple of 3. And if it's also a sufficient condition for P, that means that if the number has to be a multiple of 9, the only condition that has to be met here, I mean, it's enough that the number is a multiple of 3, and then it's enough, it's basically condition enough for the number to be a multiple of 9 as well, which is of course in this case not true, but that's the meaning of this, this thing over here. Now let's go back to our example. Now we have 2 examples over here. Let's see what these examples are, and then we have a couple of exercises validating the statements. So example number 12 is given below are 2 pairs of statements. Combine these 2 statements using if and only if. So the statements that you have are basically, for example, you have P, which is if a rectangle is a square, if a rectangle is a square, then all its 4 sides are equal. Then all its 4 sides are equal. And Q, we have if all the 4 sides of a rectangle are equal, if all the 4 sides of a rectangle are equal, then the rectangle is a square. So these are the 2, basically these are the 2 statements that we have. So the way that you can put them together, here we say that if a rectangle is a square, then all its 4 sides are equal. And then here we say that if all the 4 sides of a rectangle are equal, then the rectangle is a square. So the way that you can put these together is that you can say that a rectangle is a square if and only if all of its 4 sides are equal. So you can say that a rectangle is a square if and only if all of its 4 sides are equal. So essentially what you have is basically if a rectangle is a square, if a rectangle is a square, then all of its 4 sides are equal. So you can take this part over here, for example, and you can say that, so you can basically take all this statement over here. You say if a rectangle is a square, so you can say that the rectangle is a square if and only if all of its 4 sides are equal. So what that means is that now a rectangle is going to be a square if all of its 4 sides are equal, and also if all of the four sides of a rectangle are equal, then the rectangle is going to be a square. Both ways, it works both ways. Or suppose that you have, for example, if the sum of digits of a number is divisible by 3, if basically the sum of digits of a number is divisible by 3, if the sum of digits of a number is divisible by 3, then the number is divisible by 3. Then the number is divisible by 3. And also this is P, and then you have Q as well, which is if a number is divisible by 3, if a number is divisible by 3, then the sum of its digits is divisible by 3. And the sum of its digits is divisible by 3. Divisible by 3. So now to put these two together, you can say that a number is divisible by 3. You can say that a number is divisible by 3 if and only if the sum of its digits is divisible by 3. The sum of its digits is divisible by 3. And that's basically that. Okay, so the next thing that we have here is exercise 14.14. We have a couple more things here to discuss. So I'll see you in the next video.